In this screencast, we're going to talk about flux, where it comes from, and how you do computations. So the idea is that flux is flow across a curve instead of along a curve. So if we're flowing across a curve, then the idea is we've got a vector field, and we'll just use a radial vector field pointing outward. And if I go along a circle in this radial vector field, notice that as I'm moving along the circle, the flow is always to the right, and I'm moving out. In some sense, flow is going outward across the curve. So here we say the flux is bigger than 0. And alternatively, if things are flowing in and the vector field has things moving towards the middle, so if you think of water flowing into a drain in the middle, there's a sink right there, then as I calculate the flux across this curve, the flow is going in, and since it's flowing in, we say the flux is negative. This vector field right here would be something like the vector field xy, and this one would be the vector field negative x, negative y. And what we're going to do is just compare this with our flow. Remember, flow or work was the amount of the vector field in the tangential direction. Flux is alternatively, we're taking the amount of the vector field flowing outward, and this n right here is a outward normal vector. So as I move along the curve, rather than calculating the normal vector to the curve, rather than calculating the tangential vectors, we're going to start calculating normal vectors. And so we want to know, is the vector field going with or against that normal vector? And that's essentially the idea. Flux, sometimes written as a capital V, is just the amount of the flow pointing outward. Now, in the same way that work is, we take our vector field, m dx plus n dy, so here's your vector field f, and this is essentially your tangent vector. Using that same kind of notation, we're going to show that flux is m dy minus n dx, where here's your vector field, and now this is your n, where the negative dx is the part on the n. So n is your dy negative dx. And here the t, or the tds, is your dx dy. And the idea just comes simply from, if you have a vector, dx dy, and you want to find a vector that's orthogonal to it, then you have to dot it with something to get 0. Well, the easiest way to get something orthogonal to this vector is to flip the direction and then change the sign on one of the terms. We're going to show that it always is the second term that you have to use if you go in a counterclockwise direction. So if you move along a curve in a counterclockwise direction, pick a spot on the curve and draw the tangent vector. That vector should be given by essentially a dx dy. Notice that both of those are bigger than 0 in this picture. If I'd like to find the normal vector, then I ought to flip just flip the order, and I have to change one of the signs. Which sign should I change? Well, I need the x component. This number here still needs to be positive, and since dy was positive to begin with, it should still remain positive. Whereas the change in the y direction now needs to be negative because we're going down. Since dx was positive, we put tack on negative, and that gives us our normal vector, or our nds. So now we're going to just do an example. This is the formula we use for flux. And the example we're going to look at is we're going to take a vector field, x plus y, y. And we're going to take a curve. The curve will be a circle of radius 2. And we're going to calculate the flux of this vector field across a circle of radius 2. In order to do that, I'm going to need r prime. R prime is minus 2 sine t, 2 cosine t. That right there gives me my dx and my dy. Here's my x, here's my y, here's my n, here's my n. Let's rewrite the vector field in terms of t before we proceed. Notice I'm supposed to take x plus y, which means I need a 2 cosine t plus 2 sine t. And then I need y, which is 2 sine t. This is my m and my n. So I need m dy, which is 2 cosine t plus 2 sine t, timesing it by dy, 2 cosine t, And now I need minus n 2 sine t times dx minus 2 sine t. If I'm going to go all the way around the circle, it needs to be from 0 to 2 pi, and I need a dt at the end. That's our integral for flux. It's an integral you could calculate, but I'm going to stop right there.